Hi everybody, today we are going to be looking at measuring distance and using the metric system. We're going to talk a little bit about some distances that we use in astronomy and a little bit about how metric conversions work. The metric system, in case you don't remember what it is, it's a decimal-based system of measurement proposed in 1670 and standardized in France in the 1790s. It is based on tens. It is very nice. The units: meter for length, liter for volume, and gram for mass. Base 10 system, it means that it goes by tens. So tens, hundreds, thousands, 10,000s, tenths, hundreds, thousandths, and so on. And it uses prefixes that denote the amount. Hopefully you've got a little bit of experience with this already. It is much simpler to calculate things than using the imperial system that we use. We use miles and we use pounds, and we use things that are very tough to convert. This is just a table that shows some prefixes. So we start with length. We start with the meter. We don't really use a deca or hectometer much. That means 10 meters or 100 meters. We do use a kilometer quite often. And then there's decimeter. Don't use that much. We use a centimeter. That's 1/100th of a meter. And a millimeter, 1/1000th of a meter. Here's some metric prefixes, just in case you're wondering, in case you hear them. You commonly hear them with computers when they talk about gigabytes and terabytes and megabytes or megs. So tera is a trillion. It's a big number. Giga is a billion. Mega is a million. Thousand is kilo. And then, of course, we got the base unit. And then we go into deci, centa, milli, micro, nano, pico. And it just kind of keeps going. Okay, so going from smaller unit to a larger unit, you divide. An example might be this. 525 meters is equal to how many kilometers? Meters is smaller. Kilometers is bigger. So we know that 1 kilometer is 1,000 meters. So 525 meters divided by a kilometer, 1,000, would be 0.525 kilometers. So 525 meters is less than a full kilometer. It's about 0.525. Now, 2,500 millimeters is equal to how many meters? Here we've got 1 meter is 1,000 millimeters. So 2,500 divided by 1,000 equals 2.5 meters. Okay, so we are going from the smaller unit to the larger unit. If we go from a larger unit to smaller, we have to multiply. So 250 kilometers is how many meters? Well, kilometers is the larger unit. Meters is a smaller unit, so we would multiply. So what do we multiply by? Well, 250 kilometers. Each kilometer is 1,000 meters, so 250 times 1,000 would be 250,000 meters. So we go from the larger unit to the smaller, we have to multiply. And again, we're going from a larger to a smaller. We're going from 15 meters to how many millimeters? So we have to look up, well, how many millimeters are in a meter? 1,000. So 1,000 times 15 is 15,000. Again, larger unit to smaller unit, multiply. We just have to figure out what the unit means. In this case, millimeter is 1/1000th of a meter. Okay, converting units. I included a calculator. This is also included in Schoology. So converting, you can use a calculator to convert, and it makes this so much easier. You just plug the numbers in. So if you know that a kilometer is smaller than a mile, okay, 1 mile is 1.61 kilometers. So kilometers are smaller unit, mile is longer by about 60%. So here's an example. 1,500 miles equals how many kilometers? Well, we just have to convert. We go 1,500 times 1.61, 1,500 miles, 1.61 kilometers per mile, 1,500 times 1.61. We get 2,415. If we go the other way around, if we go kilometers to miles, and we have 255 kilometers, how many miles is that? Well, we have to go 255 times 0.621, which is the conversion that was up at the top. That was up here. And we get 158.4 miles. Now, here we're going to get into some astronomical measurements. The astronomical unit is one you're going to see pop up a lot. An AU is the average distance from the center of the Earth to the sun. So it's about, we usually say about 93 million miles is usually the conversion you're going to see, approximately 93 million. So that's an astronomical unit, the average distance from the Earth to the sun, approximately 93 million miles. Here I think it's 92,900,000. So we're going to round it to 93 million. The speed of light is approximately, this is rounded, 300,000 kilometers per second, or 186,000 miles per second. That means that light travels 186,000 miles in 1 second, 1 Mississippi. That's about a second. A light year is how far light can travel in 1 year. So when you hear the term light year and something is a light year away, it means it's how far light can travel in a year, and that distance is a long ways. 9.46 trillion kilometers, or 5.88 trillion miles. It's almost impossible to even fathom how far that is, because how do we even imagine what a trillion is? It's hard to imagine a trillion, but 5.88 trillion miles in 1 second, or sorry, in 1 year. So we're going to round off to 9.5 trillion kilometers and 5.9 trillion miles when we use this. It's easier if we just round it to the nearest tenth, or 10. So another little thing that you hear pop up, and this is something that if you've ever watched Star Wars, was always kind of a big joke, the parsec. And there they use it, it's a unit of time, but it's not. A parsec is a unit of measure of interstellar space that is equal to 3.26 light years and is a distance to an object having a parallax of 1 second seen from points separated by 1 AU. We're not going to use this very often. You can look at this chart and see if you can kind of understand what that is, but it's approximately 3.26 light years is what it really is. And that's all you really need to know about it. So how do we measure distances to objects in space? So how do we know how far things are away? I mean, we can't like use a tape measure. So what do? Well, we can use radar. We bounce a radar wave off an object's surface and time the signal. That's kind of like radar. We can use that for like airplanes that are flying around. That's how ground control knows where they all are. But that only works up to about 1 billion kilometers. That's only 7 astronomical units. It's not that far in space. That's only a couple planets away when we're talking about, going out to like Jupiter. When you get out beyond that, out to Saturn, you're already beyond it. Parallax is something a little bit different. Parallax is kind of hard to picture, but you've all seen it before. You just didn't really know it. We measure objects based on their motion relative to something further away. So if you look out the window when you're driving in a car, all the objects that are closer to you are going really fast compared to objects that are further away. They don't look like they're moving as fast. And we can use that idea to measure distances. So we take advantage of knowing the distance to the sun. So if you look at that picture, what they're doing is triangulating. We've got the Earth to the sun, and then you've got the object. Well, we already know, we use a little bit of trigonometry here, and we already know the distance to the sun, and we just can double it. So we go all the way to the other side of our orbit. So we might observe once in August and then once in February, so 6 months apart. And then what we do is look to see how far it looks like the object moved. And that's how we can figure out the parallax. Now that only works up to things that are up to 10,000 light years away. So that seems like a long ways, but in space, it's not very far. The next thing is Cepheid variables. And if you watched the previous video, we talked about somebody in there who actually was credited for discovering these. It's called a standard candle. It's an object that basically gets brighter and dimmer by expanding and contracting. And what's weird about it is stars are predictable in the amount of light they give off based on their size. So by understanding how much light they give off and when they get bigger and then when they get smaller, we can actually figure out how far they are, up to 100 million light years. So that's a long ways. That's seeing things a long ways away, but that's still not seeing things all the way across the entire universe. We have a type 1 supernova. That's a star exploding, and that is about 100 million light years. So that's getting further. It's a standard candle, and they're brighter than Cepheid variables, and they're measured due to a known expected brightness. So we know how bright that particular kind of star should be when it explodes. So again, by knowing how light dims over distance, we can calculate that distance. It's pretty cool science, but we're not going to get too in depth with it. And they occur rather regularly because there are so many stars out there. It's pretty regular that one's going to explode every now and then. So, a couple wrap-up questions. What are some assumptions we make when using standard candles that might not be true? So we assume things about Cepheid variables, and we assume things about supernova, but what if one supernova was a little bit brighter than normal? Or what if one Cepheid variable, what if it's just not accurate? We're making assumptions, and we're using our best guess. And how do we know distances to even more distant objects, like things that are over 1 billion light years? That's a good one to ask, and that's something worth looking up sometime. It's actually very difficult to do, but science has figured out a way. All right, that's it for this one.